Good morning, good afternoon, good evening, everybody, wherever you might be. Today it is my honor and pleasure to welcome our new postdoc at IMPAN, SUGATO MUKHOPADHYAY, and he will give a talk about Levi-Civita connections on Tame Differential Calculi. SUGATO, the floor is yours, the Zoom is yours, take it away.
Thank you so much, sir, for the introduction. The only issue is that maybe there was something, there was something wrong when I started the recording. Yeah, thank you so much for the introduction. Thank you for giving me this opportunity to report some of my work. So this talk is based on two joint works, separately one done with Jyotishman Bhaumik and Debashish Goswami, and one with Shuprajit Bhattacharya and Shomala Jawardar. So the following is the plan of the talk. So first we'll look at some generalities on centered bimodules. So since we'll be dealing with differential calculi on non-commutative algebras, we will be modeling our differential space of forms on centered bimodules. Next, we'll present some results on tame spectral triples, and finally report on more generalized notion of tame differential calculi. Okay. So for an A bimodule E is an associative algebra, not necessarily involutive. So the center is defined in the center of the module is defined in the following manner. The bimodule E is called centered if ZE is right A total in E, that is ZE times A is the whole of E. Just note that so this means that any arbitrary element in E we can write as sum of EI AI, and then because of the centrality of these EIs, we have that we can write anything as sum of AI EI. So this in fact means that ZE is also left A total. Consequence of this is the following fact is that if you look at E tensor E, like ZE was spanning the whole of E, so ZE tensor ZE as a set is now spanning the whole of E tensor E. This leads to the following result by Scheider. So if there is a centered A bimodule, then there is a unique map sigma such that if E and E prime are elements in the center, then sigma maps E tensor E prime to E prime tensor E. This map satisfies sigma square equals identity and also the breeding property, and as we can guess that this will be our candidate for a non-commutative flip, which is in the classical sense. So let us look at two examples of centered bimodules. So first is our motivating example, which is that if we have a compact manifold M, the space of one forms omega 1M is a centered bimodule. The actions are symmetric and the algebra is commutative. Here the map sigma can is just a classical flip map on omega 1 tensor omega 1.
Sorry, the multiplication is not symmetric, but the bimodule structure is exactly such that the Leibniz rule holds, yes?
Pardon?
Right?
Pardon? Come again?
So the right multiplication is exactly defined in the following manner that the Leibniz rule is satisfied, yes?
Yes, but if we are talking about the standard differential calculi on compact manifolds, there we do indeed have that. Like if f is a f and g are functions, then f dg and dg acted on f, they are equal. This is just a classical case.
Sorry, I ask a question. Is the category of symmetric and total bimodules a symmetric monoidal category with respect to the sigma?
It is a symmetric monoidal category, but it is not necessary that the center would be well behaved with the monoidal property, that is center of E tensor E need not be a priori center of E tensor center of E.
Okay, thank you.
Yeah, and also the center of an A bimodule is not itself a sub bimodule. It is a ZA bimodule. That is, it is a bimodule with the on the center of the algebra. So a toy example, which is that if we have a non-commutative unital algebra A, so it's the center of the algebra is always non-trivial. That is, it's not zero. So the free A bimodule is for any rank is always a centered bimodule, where the center is just by the free ZA module. If we take EI to be the canonical choice of a basis, then EIs are in ZE, and moreover, the sigma can is uniquely defined by the property that sigma can EK tensor EL is L tensor EK. So having seen this, we come to the definition of tame spectral triples. So a spectral triple AHD is said to be tame if the first criteria is that, so we are constructing our space of forms according to Cohn-Landian. Yeah. So our space of forms, the space of one forms is finitely generated projective as a right A module. So the second criteria is that consider the following multiplication map: ZE tensored with A, the tensor being over the center of the algebra. This maps via multiplication into E. So this map, we demand that this be a priori a vector space isomorphism. It will actually, once we have the vector space isomorphism, there is a very natural bimodule structure on ZE tensor A, that is multiplying something from the left, it totally ignores ZE and hits A from the left, and the right one is much more natural. So note that demanding this automatically means that our space of one forms is a centered A bimodule in particular. Next, we require that the following short exact sequence be split as A bimodules. So given the space of one forms on the spectral triple, it is like the construction of higher order forms is very natural. So define the wedge map to be what maps omega tensor omega 1 tensor omega 1 to omega 2. Then we want the following short exact sequence to split. So in particular, this means that E tensor E is equal to kernel wedge direct sum and F, where F is isomorphic to omega 2 dA as by bimodules, A bimodules. This is this condition is advised by the fact that classically the space of two tensors splits into the space of the symmetric two tensors and the space of antisymmetric two tensors, where the space of antisymmetric two tensors are actually isomorphic with the space of two forms. So if we have this split, it is possible to define an idempotent on E tensor E such that its range is exactly kernel of wedge and its kernel is F. So we denote it by Psim. It is a bimodule map from E tensor E to itself. And we demand that, so since by the second condition, our space of one forms is a centered bimodule, we demand that Psim satisfies the following property, that sigma equals 2p minus 1. So in particular, this means that P has the form sigma plus 1 by 2. So this is really the analog of projecting onto the symmetric forms, like 1 plus flip by 2. Yeah. So we look at some examples. The first one was given by Froelich, Grasha, Recknagel. It is the matrix geometry on the fuzzy 3 sphere. So like a verbal description of this would be that given SU2 as homeomorphic to S3, then we look at truncations of the fundamental representation and take it as the Hilbert space. Take the endomorphism of the Hilbert space as the algebra, and endomorphism space of the Hilbert space as the algebra itself, which turns out to be a matrix algebra, and take the Dirac operator as the truncation of the usual Dirac operator on SU2. The second example is that of a spectral triple on the quantum Heisenberg manifold. It was given by Chakraborty and Sinha. So in each of these cases, the space of one forms just turns out to be a free rank 3 centered bimodule. So, I mean, it is a, like, it's the free part is immediate from the construction, and checking that these are Tame spectral triples is really a routine computation. So now we come to a more systematic class of examples. So we look at Rieffel deformations of compact Riemannian manifolds. Assume that the underlying toral action is free, and we look at spectral triples on them. So recall the following criteria for tameness of a spectral triple. That is, this multiplication map has to be a vector space isomorphism, also an A bimodule isomorphism.
Sugato, sorry, just to double check. Just to double check I understand you correctly. So from what you wrote here, I infer that all classical spectral triples will give you examples of tame spectral triples.
Of course, yes.
Just to make sure we are on the same page. Thank you.
Yeah. Yes, I should have started with example 0. Yeah, but I mean, here we can assume. But anyway, yeah. So. Okay, so we are not assuming here. So here that is the Rieffel deformation itself. So we are just recalling the criteria. So for the canonical EN equivalent spectral triples on a compact Riemannian manifold, so we would wish to arrive. So now here assume that A is C infinity M, or maybe a dense star algebra inside it, and E is the space of classical one forms. We would want to arrive at this particular candidate map where everything's like Rieffel deformations are well behaved with so monoidally. So we would want to arrive with that. Yeah.
Hi, can you? My name is Dabrowski. Can you go one slide back? I just skipped the definition.
This
so what
one?
is the definition of your spectral triple?
Of a spectral, you mean a tame spectral?
Okay. So you start with the spectral triple. In addition, you define it to be
yes.
Okay. Good. Okay. Thanks.
So we would want that it behaves well with all the properties, and that really the center of the deformed space of one forms tensored with the deformed algebra would give the isomorphism. But the main obstacle for this is that centered bimodules are not behaved well under deformation. For example, if you look at the classical case, ZE is the entirety of the space of one forms, and ZA is the whole algebra. So this deformation gives us nothing at all. So yeah, so for this we go through a sketch of the proof as to why these are in fact tame spectral triples. So for each character M underline, let's say in Zn, we define the spectral subspace AM as all those elements in the algebra such that the total action spits out a character depending on the the character of M underline taking values on T. And so we simplify it a bit for the talk, assuming that A is just a direct sum of all these spectral subspaces. This is the spectral subalgebra, which is dense in the entire algebra, but yeah, I mean, it's still dense in C infinity M, but it's of course not the whole. And the classical space of one forms also admits, again, loosely speaking, decomposition as a direct sum on the spectral subspaces. So here, definition of EM is exactly so the beta on A induces an action on E, and replacing E over here gives us the definition of EM. Then the following map that is indeed actually well behaved under theta deformation is the following one. It is that we take the invariant subspace of E and the invariant subalgebra, in fact, of A, tensor with A. This map is, at least when we do the deformation, it will behave nicely in that it will be E theta 0 tensored over A theta 0, A theta goes to E theta. So this is the map we want to focus on. So here is why we need the freeness of the underlying total action, is that M is the action is free if and only if the quotient is a smooth manifold with is, yeah, I mean, kind of, okay, with A0 being the corresponding function algebra. So here, I mean, the action being free, that we are talking about the effective action. Like, we do not care if there are like finite periodicities, we'll just quotient out that part. So yeah, okay. So using the principal bundle structure of M over M quotient Tn, we prove that E naught is a finitely generated projective A naught module, which yeah, and that E naught tensored with A to E, this is an isomorphism. So if
again,
yes,
so
yes.
just to double check, so A0 is the function algebra on the quotient space, right? M modulo Tn.
Yes, yes, but its identification is also as the invariant subalgebra of the total algebra.
Of course, yes.
Yeah. So like, I mean, I'll verbally describe the process a little bit. If I should give details, I'll like, I have them somewhere back in the in the bottom of the slides. I can go through that. So vaguely, what we are doing here is that we show that for each AM, where M is the character on Zn, on character on Zn, what we show is that the associated the associated line bundle corresponding to the character minus M over M quotient T, this sections of this line bundle correspond with each subspace AM of the algebra A. And once we have that, we are talking about sections of line bundle. So then using the Hermitian structure, we give a finite number of sections on the bundle such that the inner product norm, they form a partition of unity on the partition of unity over the manifold, over the quotient manifold. And from this we show that in fact AM tensored with A minus M, the multiplication of this going to A0, this is a like spectral subspaces are always well behaved. So AM multiplied with A minus M goes to A0, but we with this property we show that this is an onto map. So in fact the identity on A0 always admits a finite decomposition as a product of elements from AM and A minus. Yes. Yeah. Okay. Yeah. So from this we finally arrive at this following isomorphism, and then we can perform the deformation, no problem over here. This is a priori only a Tn equivariant vector space map. In fact, this is also an A theta bimodule isomorphism. It's a map and hence an isomorphism. So next, the issue here, so we have proved, we have at least stated that E0 is a finitely generated projective E0 module, and from this we have that the finitely generated projective property of E theta is done over here. In general, it is not true that that E0 is the whole of the center, but center of E theta, but it always sits inside the center. Generically, it will be the case that these are equal, but yeah. However, due to the following diagram, what is true is that ZE theta always does satisfy this part of the problem, that if it is E0 is multiplied with the center of the deformed algebra, then it will get back the center of the entire module. And from this, we have actually the isomorphism of the multiplication map that we actually desire. Yeah. So finally, comments on P and sigma. So for the cone-Langley spectral triple A theta HD, one identifies omega 1 d on A theta. So this is a one form of the deformed algebra, whereas this is the deformation of the space of one forms. They are identified via actions on the spectral subspaces of the Hilbert space, given as this, where chi theta is the following character. The identification of the two forms, that is the deformation of the two forms and two forms of the deformation, they are dealt with similarly. So then the PCM map that was already present in our classical setup in AHD, the deformation of that is the one that produces our split, and all these are well behaved over there. E theta, tensor E theta splits into kind of wedge theta, and and moreover, sigma was in our the classical flip map, so it is easy to check that the sigma can satisfy the final criterion of tameness. Okay, but we now do a classic beat and switch. Is that in the definition of tame spectral triples, there was a priori, like once we had obtained our differential calculi from the spectral triples, we did not invoke any of the properties of spectral triples at all over there. So we just introduced this definition for future reference, that a second order differential calculus, that is, we have the one and two differential forms suffice, and the multiplication map between two one forms. And they have the exact properties that the tame spectral triple have. It is just that this is an ad hoc differential differential one form that we have axiomatized, and not something coming from a concrete spectral triple. Okay. So since we today's talk is like since the biggest target of Tame spectral triples is Levi-Civita connection, so we'll talk about matrix and connections somewhat. So a Pseudo-Riemannian matrix, of the several definitions we are taking, this one is that for a space of Tame differential one forms E, it is the right alinear map G, such that first of all we have already demanded a generalized flip map. So we say that G is symmetric, quote unquote, with respect to this sigma. There is sigma compose, G compose sigma is equal to G. And moreover, we demand a generalized, analog of non-degeneracy for matrix in the classical case, which is that we define a map from E to E star. This would be classically this would be the space of derivatives. Sometimes in our case it might be a little bigger, but anyway, so it's a map BG. What it does is it takes an element omega in E and turns it into a morphism on E, such that it evaluates eta as with this following matrix. So some examples. So of course, like these are if the space of one forms are free A bimodules, then there is a very ad hoc choice of defining matrix on them. So we choose a basis omega I and define G of Gij is equal to del Ij. This is in particular a bilinear matrix. Note that we have not demanded a bilinearity over here. This turns out to be one. And so A priori is just an invertible element K in A. We might need more positivity and other things later on. But Gij is equal to K delta Ij. This is also a Pseudo-Riemannian metric. It is not necessarily bilinear though.
May I ask a question?
Yes, please.
About non-degenerateness of this G.
Yes.
So by E upper star, you mean one-sided dual, probably.
So these our E's are finitely generated projective. What by E star I mean is that right alinear maps from E to A.
Yes. So you said that maybe I misheard, but did you say that these elements of these are derivations?
No, he didn't say it. No.
No. Over here. No.
Yeah.
In examples, I have assumed that these are free A bimodules. When I'm talking about examples,
I'm talking about the dual, one-sided dual to.
Okay. No. I didn't say anything about bases. No. And in this talk, we using the dual basis lemma, we can produce something of that sort, but we are not going to talk about it.
But
yeah.
they do not satisfy.
We can if you want to, but yes, of course.
They do not satisfy in general this Leibniz rule. These are not derivations.
No, there is no Leibniz rule invoked here. But what I please forgive me if I'm wrong, but I'm worried about the statement that you have an isomorphism of right A modules. Tomek, isn't it the case that when you have the right-sided dual, so all Holmes right A linear map from a module into your algebra A, that this is how is it the right A module again? Isn't it the left A module?
Because E is a bimodule.
Because E is a bimodule. Okay. Yeah, I forgot. Yes.
So classically, this dual is the space of tangent vector fields.
Yes, of course.
But what is in this case, I cannot imagine. Okay, thank you for the clarification.
Yeah. So as I said, that this might become slightly bigger than like the derivations picture of tangent vector fields. So this might become slightly bigger than that. So we might need to take a subspace which is a centered like ZA bimodule, something like that. It might be necessary. Yeah. So we have the examples of like on free A bimodules, some ad hoc sums. So there are enough to talk about at least. And okay, so but
sorry again, when you say free A bimodule, do you really mean freeness in the sense of A bimodules, or do you mean that your bimodule is free as a left and the right module? Because these are completely different things.
Yes, of course. Of course. Okay. So we take it to be a priori, then let us take the norm that they are free right A bimodules. But from the centered condition, we will get that they are also free as left A bimodules then.
Yeah, but you have to remember that an algebra is typically not a free A bimodule over itself. Yeah, because freeness of in the bimodule sense means that your ring over which you take the module is A tensor A op. And these are very special algebras. This was in the works of Quillen and so on and so forth. There's some Hochschild homology condition for this. So there's a whole yoga of free A bimodules. Yeah, and I don't think this is what you mean. What you really mean is bimodules that are free left and right.
Okay. Thank you for.
Sure. Just clarification.
Maybe I'll look this up afterwards. Okay, so
free. I mean, this is just algebra. You mean it's free in an algebraic sense, from the left and from the right.
Yes. Yes.
Yeah. Well, I'm just remarking. It's algebra we are talking about
here.
Yeah.
Maybe I can add to this what Piotr said, that there is a equivalence between A bimodules and A tensor A op modules. So
yes, sure.
Oh, that's right. That's correct. So, I mean, if we go back to the commutative case, we have a manifold. We have differential forms, the usual de Rham complex. Is that tame in your sense?
Yes, yes. The classical ones all are, yeah.
I see, okay. All right, good. Okay, good. Thank you.
Okay, but so even though we have departed a little bit from spectral triples, but since right now all the three examples that we have in our at our disposal are spectral triples, so we should make we have the responsibility to make a comment about what happens to the natural metric on Tame spectral triples. So this work was done prior. So for AHD or p-soluble Tame spectral triple, we define tau as the following, and then we consider we denote as S naught the star subalgebra generated by A and decommutator A, so sitting inside VH. And if one assumes that this tau is a faithful normal trace on the von Neumann algebra generated by S naught, then following Froelich-Brajois-Recknagel, one can construct an A double commutant valued inner product on A. It is defined by that. So if omega and eta are sitting inside the space of one forms, then the inner product is given by tau of, like, the values are uniquely determined as follows, but these are double commutant valued. So now
so let me maybe I can also just comment. So in the classical case, at least, these are sections of the Clifford bundle, in this case S0.
You mean of the spinor bundle? What bundle?
Clifford bundle.
Clifford bundle of Clifford algebras?
Yes.
Ah, okay, good. All right. Well, that's the same. The bundle, that's the same as differential forms. In the classical case,
as a vector space, as a vector
yes,
bundle.
yes, you are quite right. You are absolutely right. Yes,
Okay.
right.
Sorry, could you say something more about this assumption that tau is faithful normal trace? How strong is it? Given p-summable spectral triple, is it visible on the start when this is the case or not?
No, this is, I mean, so classically, one exists always, that is a different thing, but in general, it might not work out. I wouldn't be able to give an example off the top of my head, but this might not hold. Yeah, maybe I'm wrong also. Maybe I'm seeing something.
No, I'm just asking about some sufficient condition for this tau being faithful normal.
I wouldn't be able
Condition
to
which
say.
is easy to check.
Okay. I mean, I wouldn't be able to give a give the other sufficiency conditions. I wouldn't be able to check. Yeah, that is what I'm like. Sufficiency I wouldn't be able to give. Yeah, as opposed to checking individually on examples.
I see. Okay, thanks.
And so from the inner product, we define an A double commutant valued bilinear, like a form defined a priori on just the tensor over C, given as G omega tensor eta takes the value omega star inner product with eta. Using the properties of the inner product, we can see that this map descends, in fact, to E tensor E over A, and this is a bilinear map, and it takes values on A double commutant. But in order for this to be a truly genuine A-valued metric, the following sufficiency conditions were given by Goswami. So they are the following, that for like on the entirety of S naught, are going to be H defined by T goes to the following operator. This is differentiable at T equals 0. This is the first assumption. This gives from this we'll have the existence of the non-commutative Laplacian over here. So, and the assumption, I mean, I know it kind of seems like begging the question itself, but if like the A belongs to the domain of L, but if L actually maps A inside A, then subject to these conditions, the matrix G is just given by, like, so on dA tensor dB, the space of like on the one forms, it is given by this particular formula.
Can I ask you? So this first point is weaker than smoothness condition of Kohn for the spectral triples, the additional property, right? It's just differentiability at T0. Okay.
Just differentiability, yes. You're not smoothness. Okay, so just let us recall for completion's sake the notion of connections on the space of forms. So we will deal exclusively with right connections. So right connections are C-linear maps on E, which takes values in E tensor E and follows the following right Leibniz rule. And the torsion of nabla, T nabla, this so torsion of nabla is defined by the following right A linear map. And we say that nabla is torsionless if T nabla equals 0. Then we'll have to come up with what would we mean by a compatibility condition of a connection nabla with respect to G. So there are various definitions that do exist in literature. We will be giving some comparison, like not the other definitions, but some comparison results with those definitions. So if you recall that classically, if we take just a dense algebra inside A, then the compatibility of a connection with a metric can be given by in the following form. So yeah. So then our goal is to define an analog of this compatibility condition for differential calculi. So note over here that the map decompose G, like in the case of T nabla, decompose G, defining this has no problem whatsoever with non-commutativity. Well, we have assumed something about G, but yeah, there's no problem with non-commutativity. The right side over here is not at all well behaved with non-commutative structure. So, so this is something which evaluates a two tensor omega tensor eta, and it's dependent on nabla and G. So we wish to define a C-linear map. This denotes that it's dependent on G and nabla, which will be well defined on E tensor E, and it takes values in E. So mainly our goal over here is to check whether this can be replaced by sigma 2, 3. Okay, but before pi g nabla, we have to go one step backwards and start on the center of the space of one forms. So yeah, so on omega tensor eta over C, we define it as we would have liked it, replacing sigma by flip 2, 3 by sigma 2, 3, that is on the second and third leg. So just note here that this is symmetric in the sense that, like, if I had started with eta tensor omega, this would have still, the expression on the right would have still remained the same. This would be needed later on. Okay, so it is true that the map descends, in fact, on the tensor over ZA. It is mostly mundane computation. Yeah. So, okay, I mean, this completes the proof of that. And then we recall that given, we had the isomorphism UE going from ZE tensor A to E, but also while, like as we commented, that while it is not monadally well behaved, but okay, I have made a mistake over here. This should have been tensor over ZA. It does follow this particular monadal behavior, that if ZE tensor A to E is just this part is an isomorphism, then the whole of this is an isomorphism. Then using this and the fact that this isomorphism really gives a decomposition like of the fact, we define pi g nabla using the isomorphism and the previous auxiliary map pi g check nabla that we had, taking care that it is the right alinear part on pi g check nabla, and that it spits out dA as a right Leibniz rule.
Can I ask the question?
Yes, please.
Could you come back to your torsionless condition? Yes. And next page. Thank you for this. And next page. Yeah. So usually this compatibility condition between the connection and the Riemann metric is a kind of Leibniz rule. So you are reversing this Leibniz order here but you have this flip of type 2-3.
Yes.
So the action of this nabla is somehow, yeah.
Compensating for that. Yeah. So if
yes, but
what you're saying is that, so if I had written over here pi g omega tensor eta plus omega tensor nabla eta, then
yes, and then
forgetting this part, this is perfectly fine if you had it like that. And then so then over here, okay, let us fix the notation that nabla, even though it takes e to e tensor e, we just fix the notation, maybe fix the notation that it takes e to e tensor omega 1, remembering that it is a right linear map, and the second tensor and is really the honest case of one forms. Then over here, nabla omega tensor eta is an element in e tensor omega 1 tensor e. And then the flip gives us an element from e tensor e tensor omega 1, and G is perfectly okay evaluating e tensor e. And similarly, if we had omega tensor nabla eta, we would have had an element in e tensor omega 1.
Yes, I understand that this works in this way, but my question is, can you preserve the Leibniz rule kind of application of this nabla, and then maybe use some other combination of flips?
So I have not been able to prove, even in other scenarios.
So the classical calculus in this case is non-consistent, I suppose. And your choice,
you mean to say that this doesn't go back to the classical metric compatibility?
No. I'm claiming, I'm asking whether you can keep this Leibniz rule kind of this expression plus some application of some other flips to obtain the same.
Yes. Okay. So then,
it's clear to me because of course you have some symmetry in this tensor product over A, but is this symmetry? I forgot. Is this symmetry simply a flip?
Yes. Yes. Classically, it is always, and we are talking about centered bimodules. So on the central part, it is still just a flip.
Now I get it. Okay. Thank you.
So if we could have kept it as omega tensor nabla eta, and then on the first part we would have applied G tensor identity flip 2-3, and on the second part we would have just applied G tensor identity. I mean, we could have just forgotten about this. But since we do have the symmetry, we express it in this form.
So maybe I could ask further. Classically, this Leibniz rule allows us to prove that this operation is well defined. Okay, because on the right hand side you have a tensor product between omega and eta. Okay, on the left hand side you have a tensor product between nablas of these two with eta or omega respectively. So how to check using this this definition? How to check that this is well defined?
So I have not yet. So when I say this, I am just recalling the classical one. I have not yet defined what my pi g nabla would be for the Tame differential calculus case. That is what I was doing next after this slide. Defining that something like this can actually be well defined.
So you have a result claiming that this is well defined.
A form of this is well defined.
It is consistent with the derivation property of nabla.
Yes.
Okay. Yes. Thank you.
Yeah. So. mm, Yes, like you were saying that the derivation property. So what you were saying is that in the right, like both hand sides have the right Leibniz rule, so that if you have LHS minus RHS, that is actually an A right linear map. That is one of the upshots of that, I think, or I mean, maybe, yeah. Okay, so
Sorry, I was only
yes.
worrying if you apply on the left right hand side omega times A tensor eta minus omega tensor A times omega. Is tensor eta, sorry. I was worrying what is happening on the left hand side.
Yes, yes.
Is it automatically killed by the balancing over A? Is it automatically killed on the left hand side?
Yes, yes. So
okay,
that was part of the proof that I was going through. That
Thank you.
Yeah. So like the left hand side is defined on E tensor E. We use the isomorphism over here to decompose it into center tensored with here. I have a major mistake over here. This should have been ZA. Center tensored with the algebra. The inverse is well defined, and here we have really the whatever is the left hand side, what we mean by pi g nabla on the left hand side, which is that for like if we have omega tensor over A eta tensor over eta A, and then it comes out once as a right linear map, and A comes out once as the derivative. So the right Leibniz, maybe, or maybe I'm still misunderstanding what you wanted to ask, but yeah.
No, I believe that it is well balanced, well defined for this over the center. But I was worrying what is about balancing over A.
Yes, so
on the left
that, yes, on the left hand side. So that is what I'm saying, that here I mean this like defining first we had proved that this part is well defined, that descending on ZA is perfectly fine, and then we added the algebra from the right and show that this is actually well defined using the isomorphism.
Okay, thank you.
So then, okay, I should have made a, anyway, it's information dump. So then the left hand side minus the right hand side, so which were both right Leibniz, they turn out to be a right A linear map, and we say that a connection nabla on E is compatible with the Pseudo-Riemannian metric G if the right A linear map given by pi g nabla minus decomposed G, this is equal to 0. So, and if we say that nabla is a Levi-Civita, if it for the tuple EDG, it is also torsionless. Then we come to the statement of the main theorem.
Can you just remind, so it is a linear map from where to where, this combination?
Yes, I should have written it somewhere. Yes, so this is a map from E tensor E to E.
Okay.
Yeah.
Okay. So despite that there is D there, it cancels the higher.
Yes.
So, okay.
Yes, I mean, you could say in our case by construction, but our case also reduces to the classical one when we take manifolds, and classically it also happens. That is cancels the left and the right cancels out the right. Then we have the theorem that suppose ED gives a Tame differential calculus on the algebra, and G is very importantly like right for the moment it is just has to be a bilinear map that we also demand alinearity. So G is a metric on the space of one forms. Then for the tuple E comma G, there exists a unique Levi-Civita connection for the pair. So we will go through a sketch of the proof. So, okay. So first we recall the decomposition of E tensor E.
Sorry for that.
Yes.
Can you one slide back again? So, okay, so next. Okay, so what is then next? Okay. And no, there was something on the previous transparency, which.
Here?
Okay, yeah, but I don't see it.
No, I mean, I can go through and show you if I think this was.
Okay, go on. Yeah. Okay, sorry.
So we recall the decomposition in the definition of Tame spectral triples, and where wedge restricted to F was an isomorphism, we start to denote this kernel of this wedge map by E sim E. We recall that E sim E was the range of the idempotent P sim, and we note that it is invariant under sigma. So sigma being involutive, applying sigma P sim just leaves P sim again. Then we define a map nabla naught as minus of, so this isomorphism restricted, so restriction map being an isomorphism, minus of wedge inverse composed D. This is a map from E to E tensor A. So it is easy to check that this is a torsionless connection. First of all, the Leibniz of D will help give the right Leibniz of connections. And for torsionless, finally, we just blankly apply wedge everywhere, and we get back the usual definition of torsionless. So like wedge composed nabla naught plus D equals 0. So we have constructed one torsionless connection nabla naught. Next, we look at the set of all right connections on E. We call them con AE. So these are affine in the sense that if we have two connections nabla and nabla prime in con AE, nabla minus nabla prime is actually a right alinear map from E to E tensor A. Moreover, if nabla is also a torsionless connection, so we have already produced one, then wedge composed nabla minus nabla naught, this is equal to 0. So the range of nabla minus nabla naught is E sim E. Then in fact, maybe abuse of notation, but we can view nabla minus nabla naught as a map in Hom A, E comma E sim E. Okay. So for step 3, we recall that we had given this particular metric compatibility condition pi g nabla minus D composed G equal to 0. So for all nabla in con A, we define the following map. We have already our nabla naught. So phi g of nabla minus nabla naught, this will be equal to pi g nabla minus pi g nabla naught. Now, is this a priori well defined, etc.? So note that pi g nabla minus decomposed G minus of pi g nabla naught minus decomposed G. These are two very well defined elements in this set, as you're asking that what is it a map from where to where. So this entirety total thing is in fact a right alinear map from E tensor E to E. Okay, so now thing I had noted before, that when we were defining the auxiliary map, there was a symmetry involved on how it acts on omega tensor eta. So because of this, we can restrict the map to the invariant submodule under sigma, and view this as a map from Hom A to E sim E, Hom A, E sim E to E. Okay. But now you see we have a map in one over here and one over here. One is nabla minus nabla naught and one is phi g of nabla minus nabla naught. Then we are asking to look at the map phi g itself as a map from this Hom set to this Hom set. So suppose phi g is an invertible map. Then we define nabla g to be nabla naught plus phi g inverse on decomposed g inverse pi g nabla naught minus nabla naught. So applying phi g on each side would really explain why this construction is like a reverse calculation of sorts. So it will show that nabla g in fact okay, first of all I have to say why it is a connection. So as you mentioned that the space of right connections is an affine space. This is one connection, and this entire thing is a right linear map. So nabla g is a connection. Applying phi g all over will give us the metric compatibility condition, and we have to like work with wedge a little bit more to get that this is a torsionless connection. But so the question remains is that is phi g an invertible map? Also uniqueness will also come across that if we have another nabla prime, then uniqueness will come from this only. Okay, so now we look at the following map. So we had P sim from E tensor E to E tensor E. We look at identity as a P sim on 3 legs. So first of all, note that P sim maps onto E sim E. And then we can also restrict the map and restrict the domain of the map. To get this, there is an abusive notation. We should have written restriction over here. Now, it's not, I mean, happenstance that we're talking about this. We'll see in a while via commutative diagrams why we want to talk about this. Okay. So the proof of the invertibility of phi g involves showing that if this restricted domain codomain map is an isomorphism, then phi g is invertible, is an isomorphism, hence invertible for all g. And if phi g is invertible for just one bilinear g, then identity as a P sim is an isomorphism. I mean, in this restricted sense, it is an isomorphism. Hence, for all g, it is the Levi-Civita will exist uniquely. Okay. So this is the commutative diagram which led us to the to asking for this isomorphism. So note here that we have on the top we have the phi g map. Here we have the identification that if we have two bimodules E and F, then Hom A E to F is F tensor E star being right A linear A valued maps. Next, we invoke that when we were defining metric, we had said that Vg for us needs to be invertible. So this descends the space down to E sim E tensor E. We apply identity tensor P sim on this on the restriction map over this to get inside this space over here. Now, what is VG2? I have not mentioned. Again, if someone wants, I'll go back in the bottom of my slides. But VG2 is somehow constructed on like 2 copies of VG, and the invertibility of VG implies that this is an isomorphism. And yeah, this. And finally, we have the canonical isomorphism between the Hom set and the tensor. It is somewhat laborious to check that this is a commutative diagram, and also to check that this is a well-defined map. To see that this is a priori well-defined, a sufficient condition was the bilinearity of G. That is where we are in this leg is where we are using the bilinearity of G. So all these 4 maps are all isomorphisms. So the isomorphism of one would of the top one would imply the isomorphism of the bottom one, and vice versa. Yeah. Okay, but then is this restricted identity an isomorphism? So yes, that is true, because PSIM was sigma plus 1 by 2, and sigma sat is both involutive and satisfies the breeding relation. To check that this is an injective map is pretty easy. I mean, if you go back one step, we take an element X here, which is in the eigenspace of sigma with sigma 1 2 with eigenvalue 1, and then applying the breeding relation on over here will give a triviality that when X is like if when identity PSIM on X is 0, this implies that X is 0. So injectivity is easy. If we had free bimodules, in the sense that they are A tensor Cn, some C to the power n, then surjectivity would also be equally trivial. For the fact that these are indeed surjective in the finitely generated projective case, we have to work with dual basis a bit. But yes, at the end, it is indeed true that the restricted map identity PSIM is an isomorphism. So this proves the theorem. So I will now go on to some intermediary results that we have. Oh, okay. So no, first I had promised some comparison results. So
can
yes.
we ask about this theorem? So this the assumption is that G is a bilinear, right? Did I understand properly?
G is a bilinear, both left and right bilinear.
Very strong condition.
Very strong condition. Yes.
And non-commutative case is really okay. And then also the sigma then probably
sigma is also very rigid.
Very particular one. Okay, probably just twist or some theta deformation of twist. Okay.
Yes, really there is no non-commutativity on the module. It's just on the algebra.
Okay.
Okay. So by virtue of the main theorem so far, what we have is that we want to compare with results that already existed, some results that already exist in literature. So for Froelich, Raja, Recknagel, they had defined something called a real unitary connection in general, and they had shown that there is a unique torsionless real unitary connection on the matrix geometry of the fuzzy 3-sphere. So the connection that we this is with the canonical bilinear matrix on the spectral triple that we discussed. So
well, I think the natural question here is once you have done this, so you have this idea of the Levi-Civita connection, for tame spectral triples,
Mhm.
is there then some very natural Gauss-Bonnet theorem? I mean, that I think is the question at this point, in my opinion.
So I like my last four slides.
You
make
have a
some-
Gauss-Bonnet theorem for this?
So my last four slides make some comments on that. We don't have a very blanket statement, but we do have some results on that. Like
You have
very
a
kind-
conjecture, a formulation of what the Gauss-Bonnet theorem should be?
No, we are so.
Let's wait. Let's wait. If you arrive to the last four transparencies.
We shall wait. Okay.
No, we don't. It's mostly qualitative discussion. It's nothing nothing very rigid that we are talking about. But yeah, we have something to at least offer, maybe. So yeah. So for the canonical metric on the spectral triple, their connection and our connection coincide. So using the prescription of unique torsionless unitary prescription of torsionless real unitary connections on quantum the quantum Heisenberg manifold. So Chakraborty and Sinha constructed a spectral triple over this, and they showed that there can be no connection which is both torsionless as well as real unitary in the sense of Röhlig eta. And finally,
And in your sense,
yes. So I had mentioned that the
that it is.
spectral triple
It
is a tame spectral
Okay.
triple. Yes.
Okay.
So I mean, we can't compare with them because they don't have any. Our comparison is that we have one. Yeah. So and our comparison result for the total Riemannian manifolds with the assumption that the action is free is that our Levi-Civita connection is the deformation of the classical Levi-Civita connection. So I mean, yeah. So I mean that is what we would naturally expect. Okay, so now to some intermediate results before we can talk about Gauss-Bonnet. So this is a I'll just there's no point in So this is an interesting example of tame differential calculi in the sense that this is not coming from a piece-able spectral triple. So here Dirac triple, let's say, so on the Kunz algebra with 3 generators, the following triple was defined that with the KMS state, this following Hilbert space was defined, and delta I was defined as follows over here with the action of each of the basis elements xi of the Lie algebra, and sigma I are the Pauli spin matrices. Then decommutator pi a actually becomes a separating derivation, let's say, where I mean in the sense that so the space of forms actually do make up a tame differential calculus, and it's a rank 3 free module. So we have over there, and so here we have a comment to make regarding bilinearity, which is that we define something called strongly sigma compatible matrix. So the following has to hold is that if you have 4 elements in E and then define G2 on the tensor of the 4 elements in the following manner, that the middle 2 elements are first evaluated by G, and then the evaluation on the remaining 2 tensor, that that remains behind. Then applying the flip on the first two elements would be equivalent to applying the flip on the last two. And this is just for right alinear maps, right linear matrix. So this is a relaxation of the bilinearity condition. So there is the following result that this theorem as before, except for the fact that instead of a bilinear G with a strongly sigma compatible Pseudo-Riemannian metric, the unique Levi-Civita connection result also holds. The proof is exactly the same in the commutative diagram that I had shown. The one leg where we needed to use bilinear, like bilinearity was a sufficient condition, this removes that blanket clause. So examples of strongly sigma compatible metric. So first of all, yes.
Can I again, sorry for that, but it's interesting anyway. So the pseudo-Riemannian, but in this case, it's just Riemannian. You had some pluses in this form for the Dirac operator, right? It's just Riemannian. Can you get pseudo-Riemannian metric here?
Pseudo-Riemannian in the sense that we are not demanding positivity or something like that.
Okay. Explicitly, though it probably comes in this exam. Okay, thanks. But Mike, okay, so in this formula for the Dirac operator, you could put some minuses in this expression instead of pluses?
Yes.
Okay.
Yes, we could have put yes. So the zeroth example is, of course, of bilinear pseudo-Riemannian matrices. For this, the strong sigma compatibility always holds. The second one is that if we have any bilinear matrix G and an invertible element K in A, then the deformation KG, that is the evaluating on omega and eta by this thing. This is a strongly sigma compatible matrix. And something weaker than that, like we realize that we can play a little bit more, there's more freedom to play with. So the following metric is also a sigma compatible metric, that is choose a basis and then focus on the diagonal. We put a K in the first component and one diagonally on all the others. Then that is an example of a strongly sigma compatible metric. So in particular, I think, but yeah, so in particular, this would define a class of slightly curved matrix on the non-commutative tori, in the sense that maybe we could hope for non-zero scalar curvature. Yeah. So yeah, these are two intermediate results. And then we come to something more, which is that so far we had not had Christoffel symbols for our Tame differential calculi, which was pretty disappointing. But now with the assumption that if the space of one forms is a free bimodule over A with a central basis E1 times En, this holds in except for the except for not all the Rieffel deformation examples, mostly our examples are right now free bimodules. So if the space of one forms is free and G is a strongly sigma compatible metric, and the external derivative is given by dA is equal to sum over I ti a ei. This is part of this comes free with the free module thing. So in terms of nabla knot, which are explicitly constructible, we have the following technical expression for Christoffel symbols. Okay, I've made a mistake here. This should have been gamma naught. Gamma naught is the Christoffel symbol for nabla knot. So yeah. Okay, moving on. Then some of the standard expressions that we didn't have explicit, like not explicit, at least closed forms for, we now can, we know that there are explicit forms for these. So we have the curvature operator. In our preprint, I think we have missed a negative sign, but anyway, I'll have to check. So yeah, we have this. We can find out about connection one forms from like given a metric, we can find the connection one forms on our calculus. We have curvature two forms. So omega ij defined using the curvature operator with the following expression. This tameness comes is applied heavily over this, and particularly omega ij that it satisfies. I've made something this is an error here. Yeah, so this heavily uses tameness and Bianchi identity. So these are some things that we can now make a comment on. And some new examples. So we had seen with the example on the Kunz algebra that we are also interested in non-p-simable spectral triple data. We are still learning about spectral triples as well. So this is the following, that given any algebra A which is finally generated by SIs, which admits a total action just diagonally on the generators, then we can always define a exterior derivative in the following manner, which will give a free calculus, and the higher order, like the wedge map, the higher order will be induced by just the trivial Lie algebra relation on the Lie algebra of Tn. I have again made a mistake. There's a Tn over here. So we have obtained a toy calculus a priori on the free group algebra. So we have checked that it is covariant under with respect to the co-commutative co-multiplication of the underlying Hopf algebra. And for ON, the last time the action was done by SO3, we have produced another Tame differential calculus on ON using the Tn action. So these are some things that we were playing around with, just to find more examples of Tame calculi.
Sugato, sorry to be nagging again, but I cannot resist the temptation. When you look at these beautiful Kunz algebras, they are precisely examples of algebras over which free modules have no rank. So when you just before used a phrase, free module rank n, it immediately a red light flashes in front of me.
I think I am making
You're saying a free module over ON, the rank is not well defined?
Exactly, yes. I mean, if you have a free module, you can have a basis with different number of elements. So
it doesn't have IBN, you are saying so.
Exactly, yes, exactly. Invariant basis property, exactly. Yeah, precisely. It has no finite dimensional representations. So this is why such things can happen.
Right. So yes, so we had at one point a few years back thought about IBN, and if IBN is an issue cropping up, I will look into it and see if there's something gravely wrong that we are doing. Yeah.
But you can use any basis.
Yeah, surely, yes.
So the rank of this module is irrelevant.
Exactly, but that's why this is just an unhappy phrase to say, well, let's take free module of rank n. I mean, you just need a free module. That's it.
Okay.
Yeah.
So Paul, here in this example, is On to power n is isomorphic as a module to On itself.
Can you repeat? I can't hear you.
Yes, yes.
On
Yeah.
to power n is isomorphic as a module to On itself.
Well, On to power, you mean adding it to itself.
Exactly, yes. So
Okay.
it's a free module, right? You have two free modules, they are isomorphic. And this is precisely using this relation.
Uh-huh. Oh, I see, okay.
Okay.
But then the question arises, if you have all your formulas
Mhm.
With a fixed rank,
Mhm.
what is happening if you change the rank?
Mhm. Right. I'll have to check what is the
Hello?
issue with this. Yeah.
Hello?
So, and then I'm scared with the, I mean, this is more us exploring, and maybe like I would benefit if somebody commented on any of this. So, so now we are assuming that we have a Tame differential calculus with separating derivatives coming from the action of T2. We are leaving aside O2 for the moment then. And then we affix it with a fixed metric K delta Ij on the calculus. Then using the curvature tensor formulas and other stuff, we can calculate that the scalar is the scalar curvature has the following form. Why it's not like this? It should have been signed over here. Anyway, yeah, this has this particular following form. So classically, the Gaussian curvature of a surface is half of the scalar curvature. So we would really like to say define a K which is equal to half of scalar. And moreover, we are once we have a Tame calculus coming from the action of T2, then the rank dimension of the second order, like the second order differential forms has a single, like is generated by a single element. Right. So the natural one for this choice of a metric would be equal to this one. Yeah. So retaining the assumptions made in the previous page. So if omega 2a is generated by a single element, then any two form theta has like is identified with some unique a, and like a choice of minus E1 wedge E2 or E1 wedge E2 defines an orientation for us. Then if there exists a tracial state, one could define the like on like integral with respect to the volume form as tau of a. So we have the following proposition, which is that if tau be a trace on a, if it exists at all, and G is equal to K delta Ij, defined where K is positive invertible, then the curvature 2 form omega 1 2 satisfies, first of all, it is antisymmetric, and with respect to the tau, it's omega 1 2 satisfies this. So we would really like to be able to call this, we are like very hopefully calling this a Gauss-Bonnet 2 form corresponding to the deformation parameter K. Then for each K we get one such omega 1 2, and moreover we shall say that the rank 2 calculus with the trace tau satisfies the Gauss-Bonnet theorem if this integral is independent of the smooth deformation parameter K. but yeah, I mean, we are not making a statement about the Gauss point, but we are beating around the bush about it a little bit. And so we have some identifications that we made. So for example, if K1 and K2 were two parameters, we have this relation, which essentially says that if the calculus were to satisfy Gauss point, then this would have to be equal to 0 for all deformation parameters. Deformation parameters, yeah. And so from Rosenberg's Levi-Civita on non-commutative tori paper, so we have an analog of one of the results, which is that if the algebra A has a trivial state which is invariant under the Gauss point toral action, then in our sense, that invariant sense, that the calculus satisfies the Gauss point theorem. And this entire statement is now suspect because I do not know about O2 enough clearly. Is that the condition of existence of a trivial state is not necessary one. So the invariance of the KMS state under the toral action also means that integral omega k1 to is 0 for O2. So that is all I had to say.
Okay, thank you very much. Okay, any further questions?
So
Yes.
can I?
Okay.
Yeah, go
So
ahead.
Ludwig, hi. So if you have tame spectral triple, then you have con calculus, so with a commutator, with the Dirac operator, which satisfies all your properties. Understand, right? Correct.
Yes. No. So some. So no.
Not all.
No. We are not claiming that all cone differential calculi are tame. No. We are not claiming anything like that.
No, but the calculus with the commutator of the on algebra and then extended to.
No, I understand what you mean by constructing a calculus on a spectral triple. I am saying that the conditions, like we are still. I mean, it is a definition of ours is tame spectral triples, where the definition, the demands we make on differential calculi are the same demands we make on the differential calculi coming from the cone differential calculus. So
So you have to add some additional properties,
we have
right?
additional comments.
Okay.
Maybe I should go back to the definition of a tame spectral triple, or I mean. So yes, so this is what we have to say about spectral triples.
Okay, so maybe I'm lost. So then, in order to have uniqueness of the existence and uniqueness of the Levi-Civita condition, which condition you have to add?
No, the entirety is what we are asking for. This means tame, and a tame calculus equipped with right now a strongly sigma compatible metric gives a unique Levi-Civita.
Yeah, but I mean, we believe that Dirac operator yields some metric, right? So
yes. Oh, okay. Do you mean that from the Dirac operator is there a metric? So for that we gave the assumptions like which already existed. Oh. Where is it? Yes. So like we punched two of existing results, one being by Froelich, Raja, and Recknagel, like two sets of assumptions. One is that the following thing occurs. So this produces a double commutative valued inner product. We construct a double commutative valued bilinear metric from that, and then from some conditions that already existed, like applying results from before, we say that if this set of conditions is satisfied, then we would have a metric given by this. So yes, so if in order to get Levi-Civita from the canonical Dirac operator, we need even more assumptions.
Okay, understand. So I mean, one would like to have for a class of Dirac operators, maybe to have some reconstruction theorem that you could get one metric, and in your sense, among them, some of them have torsion condition satisfied and so on. This would be nice.
What do you mean by a torsion condition? I didn't understand. Could you please repeat?
Well, the reconstruction theorem of Kohn says that you can reconstruct metric.
Oh, you said
not all of them.
Okay. You mean given a metric, can I go back to a Dirac operator?
And both ways, both ways. According to Kohn, when you start with D with some properties, okay, classical case commutative algebra, you get metric. Among of them, there is one which has torsion 0. I mean, Levi-Civita connection torsion 0 of it. And then you can go back, construct the Dirac operator again from the metric. So there is kind of correspondence.
So we have not really looked at the opposite end of what you're saying. That
understand it's hard. Yeah, it's still hard to to grasp, but okay, I understand. Right. Okay, thanks.
Mike?
Can I ask?
Yeah, go ahead.
Good. So I have some problem with your second order calculus, because for the point of view of the first order calculus, if you embed differential forms, classical differential forms, into the Clifford algebra, then the relation between functions and differentials is preserved. But this Clifford multiplication, this Clifford embedding of forms into Clifford algebra is not an algebra map. So I'm a little bit confused, because you try to do what we usually do in Riemannian geometry to differential forms. You have this symmetrization and anti-symmetrization, but you apply it to something which is not the module of differential forms in the classical case, but the image of differential forms in Clifford algebra. And this changes a lot. For instance, this commutation and anti-commutation. Okay, so I'm confused. I don't understand how your operators of symmetrizations, for instance, and anti-symmetrizations, how they correspond to classical operations on differential forms. I'm not talking about their image in the Clifford algebra. So you are taking symmetrization and anti-symmetrization in the Clifford algebra, in fact.
Yes. So a priori on 2 tensors and not on E2.
Yeah.
Like 2 tensors, and how I am applying symmetrization and anti-symmetrization on that.
Yeah.
That is your. Okay.
So because you are in the Clifford algebra, and in the Clifford algebra, differentials do not anti-commute. There is, there's this scalar product can be defined by the anti-commutator. So you have some corrections to classical formulas, and they are not present in your assumptions, in your definitions.
I'm trying to understand like how we are getting away. So this is nothing. You are not asking about the result, the effect that the anti-symmetrization map has on the two forms, or is that what you're asking about?
Yes, symmetrization and anti-symmetrization.
So on the anti-symmetrization. So yes, the thing is that first of all, when we are constructing the space of forms from the spectral triple, then when we are checking if one of our examples are like at least the non-spectral triples, which the ones we made, we are checking. So we have to take care of the junk forms over there, and then it is a matter of checking whether a spectral triple is tame or not. And I mean, the examples that we have, like we have had examples, even trivial ones, where it is not the anti-symmetrization is like the naive anti-symmetrization is not well behaved. So we have things like that. So
so it could be that in some examples your assumptions are fulfilled, but your recipe doesn't reproduce what we do in Riemannian geometry.
Okay. That would mean that there is
a strange, but okay.
Gap in a proof. Gap in the proof. That would necessarily mean yes.
But then I have a problem with naming everything as we name analogs of these things in the classical Riemannian geometry, because you are using this name of torsion, this compatibility with metric, and in every place there is you are dealing with these objects as they were tensors, like differential forms, but in fact you are now in the Clifford algebra. And
right, okay,
yeah,
okay.
So for me situation is very complicated. I don't understand what is happening to these correction terms, differing exterior multiplication of forms and multiplication in the Clifford algebra. Yeah. I would like to understand this better. Yeah, maybe I have to study your paper.
You guys can meet at IMPAN. Let's now let's allow Andrei to ask his question.
Okay, yeah, thank you, Piotr. Hi, SUGATO. This is Andrei Shitas. Two questions, maybe three, but two at least. So first question is, and maybe this is expanding something on what Ludwig said. Well, you basically use the spectral triple and the same spectral triple to have a differential calculus. And then your construction is basically purely algebraic. So then you have the differential calculus that comes from the Dirac operator. Then you can define a family of metrics. And then the question is, can you go back to whatever Dirac operators these metrics define? Because that might be different Dirac operators, different structures than what you started with. So classically, this is like that. So say on S1 or whatever on the torus, a flat Dirac operator gives you a differential calculus. Then you can have a family of metrics and then give you back different Dirac operators. Can you do it here?
I have not been able to do it yet. No.
Okay. The second question is partially related. This question by Paul Baum, about the Gauss-Bonnet theorem, this is very good. Because this is, some sort of a test, whether one's doing something, relatively similar to what's been other computations, also the spectral ones for the non-commutative tori, for instance. For instance, how far can you go with showing this non-commutative version of a Gauss-Bonnet? I mean, does it work only for the conformal rescaling of the torus, or can you go, I mean, for instance, for this sort of different metrics are the partial conformal rescaling. We did a paper with Ludwig and with on something which was asymmetric non-commutative torus. So can you have metrics defined in this way, something like this asymmetric non-commutative torus or not?
So we have at least one example on the so two torus or any other algebra, our the space of forms is almost similar. So we do have at least one example where what we are saying as admitting the Gauss-Bonnet theorem, that the integral is constant, that fails to hold.
Mm-hmm.
So that is why we would like to reserve a comment on what like a more definitive statement would be, like if we need to modify our understanding more. So yes, so we do have an example where like for two different metrics, we are getting back two values on the respective curvature forms. Yes, so
Okay.
then according to us it wouldn't be.
Okay, and if Piotr allows me, last question. I mean, the entire theory is sort of much dependent on the thing that you have this central forms that basically generate the bimodule of one forms as left or right module. So beyond that, the theory doesn't. This approach would not work. No. Okay. And since this is, I mean, this is very much, I mean, to some extent similar to the approach that's been in the past, that was the connections over the center of the algebra by Michel de Bouin-Viollet and I think Peter Micho, I mean, maybe. So what, is there any relation to that, or? So
as far as I have read is that the modules that they consider are central in the sense that like the center of the algebra commutes with the entirety of the module, like that is the definition of centered, which is much more relaxed than our the notion of centered bimodules from Slider that we are taking is much more rigid than that. Yes, so we have not but the thing is that because we are applying things like metric compatibility and we are looking for a generalization of the flip map, so such a, like if we had bicovariant calculi, we have one which is sigma, but in general central bimodules we do not have that sigma available very readily. So our choice that we started with centered bimodules was a priori the
to have the flip
existence of a sigma. Yeah.
Okay. Thank you very much.
Okay. Anybody else? Adam, are you happy?
Yes, I am.
Mark, there is so much about Rieffel deformation.
I was enjoying it. I'm happy.
Okay, Mark is happy.
By the way, one more question, a very stupid one.
Okay,
if
fire at will.
Yeah, well, easy one, yeah. I mean, you can make the Rieffel deformation not only on manifolds. I mean, if you have a spectral triple with the action of a toroid, you can also. So is it a Rieffel deformation of a tame spectral triple, Just in general, not from the starting.
This is a very nice question. Yes.
I would assume so, but
yes, yeah.
So the issue here would be, so basically with the algebra, so so you want now the algebra to come from not a manifold but anything.
Yeah,
so
exactly.
our method at least would say that this A0 contained inside A, this would have to be a Hopf-Galois extension. So we would really need that all the like just one suffices. So A0 times AM going into AM, like even so A0 A1 is sufficient. So this would have to be an onto map. So yeah, we would need something like a Hopf-Galois in order to
yeah, of course, freeness. You needed freeness.
Yeah, of action. Yeah.
That's all right. Yes.
Yeah. Well, okay. Thank you very much.
And probably the Dirac operator must be invariant on the first.
Yes, of course. Then
Richard, how about you?
I'm happy.
He's happy. Okay, so in this case, if there are no further questions, let me make this very quick comment for SUGATO. The paper which I was talking about was a famous paper by Kuhn and Quillen from 1995. I was studying it when I was a student of Mark. It's called Algebra Extensions and Non-Singularity. This is Kuhn and Quillen, Journal of American Mathematical Society, 1995. And over there you can learn such things, that it's very hard for an algebra to be even projective as a bimodule. So you should really avoid, because it's confusing and in fact incorrect as stated when you say free bimodule, because when you say free bimodule, it means that something is free as a bimodule, okay? And an algebra is basically never free as a bimodule over itself. To be projective, it has to be separable. So an algebra A is separable if and only if it is projective as a bimodule. Yeah, and this means that you have to have a splitting, a bimodule splitting of a multiplication map. And because the bimodule splitting, it means that you have some funny element here, a sum over xi tensor yi, which not only that when you multiply you will get a 1, but it will also satisfy. It will be a separability element in A tensor A. So if you multiply from the left, it will be the same as multiplying from the right. So such a commutant will vanish. And this is a very tough condition. And so you basically find out that these are just matrix algebras. And when this separability condition is of the form, you take elementary matrices Eij, tensor with Ej I, and then sum over Ij. Yeah, so this is why matrix algebra is projective as a bimodule over itself. But because you are finite dimensional, separable algebras have to be finite dimensional, then I believe that there are no free algebras over themselves as bimodules. Anyway, so this is just so that you understand that saying that something is free or projective as a bimodule is an extremely strong condition. Okay, and that's not at all what you mean. You are talking about bimodules that are left and right free. All right, good. So let's thank SUGATO again. Where is this icon for clapping hands? I think that this was a nice discussion. I stop recording now.